When a help desk agent gives a bad answer in production, most development teams immediately try to debug the language model. But the model is only the final step. An agent's apparent intelligence is actually a downstream artifact of 6 distinct architectural layers interacting in real time: platform, knowledge store, tools, system prompt, memory, and model. A failure in any single upstream layer will propagate downward. If your retrieval returns garbage or your tool definitions are fuzzy, the entire stack flickers. The final output looks broken, even when the model itself is operating correctly. Today, we are wiring these 6 disparate components into a unified, resilient help desk architecture that actually runs end-to-end. Debugging a language model's text output without auditing the preceding stack is a failure of system architecture. To fix the agent, you have to fix the flow. This diagram shows the operational rhythm of a help desk agent on every single turn. It follows Anthropic's 4-phase loop: perceive, reason, act, and reflect. The input phase is perceive. On every turn, the agent aggregates the customer's current query, their identity data fetched at the start of the session, and the recent conversation history. Next, the agent has to reason. This is a strict 4-way decision matrix. The agent must choose to answer directly, call a tool to gather more data, ask a clarifying question, or escalate to a human. Once the logic path is selected, the agent moves to act. It executes the tool call, sends the response, or flags the routing system. Finally, the agent must reflect. It evaluates the success of its action strictly based on the signal from the customer's subsequent message. Did the answer actually address the problem? Optimizing this exact 4-phase loop to run deterministically across thousands of interactions is the core requirement for scaling production help desk agents. Most builders write system prompts as long, paragraph-heavy narratives. In production, large text blocks make it difficult to pinpoint which instruction the model is prioritizing when it ignores a constraint or hallucinates a policy. A production system prompt requires strict modularity. It must be broken into exactly 5 distinct sections, roughly 350 words total, with each section answering a specific question the agent asks itself on every turn. Section 1 defines the role. It needs to be exceptionally brief, 2 to 3 sentences maximum, clearly specifying who the agent is and who it is helping. Section 2 covers operational rules. These are standing instructions the agent follows turn after turn. They must be written as discrete bullet points, not paragraphs. Directives like always cite the article URL. Section 3 provides tool guidance. It governs cross-tool sequencing to prevent execution collisions. For example, instructing the agent to always run a customer lookup before searching the knowledge base. Section 4 establishes anti-goals. These are negative constraints that explicitly tell the agent what to avoid, like inventing pricing or promising refunds. Section 5 outlines escalation rules. You must provide explicit triggers for human handover, such as the user asking the same question 3 times or expressing frustration. These modular prompts allow for strict deterministic traceability. When the agent acts, you should be able to point to the specific sentence in the prompt that dictated that behavior. Information changes at different speeds. When you force fast-moving, immediate conversation data to collide with static organizational rules, the system chokes. Mixing these memory update speeds creates a severe architectural risk. It forces the system to either rely on stale data or burn capital on unnecessary database lookups every single turn. To isolate these refresh cadences, you must implement a strict 3-tier memory architecture. Tier 1 is conversation memory. This updates every turn. The runtime SDK handles this automatically, loading prior turns and compacting older ones when the context window fills. Tier 2 is customer memory. This is account-level context fetched at startup. If it needs to be updated mid-conversation, the agent executes an explicit tool call. Tier 3 is organizational memory for company-wide policies and active incidents. Because it updates rarely, it is loaded dynamically via skills, folders of scripts and resources the agent pulls only when relevant. Strict separation of these memory cadences prevents context window bloat and guarantees operational accuracy across the entire fleet. There is an assumption among builders that deploying the smartest, most capable frontier model is always the correct architectural choice. In a help desk environment, that instinct is wrong. Forcing a multi-hop reasoning model to execute simple tasks incurs massive latency and token cost penalties. Extended thinking doesn't help when a customer just needs a password reset. This table compares latency and cost metrics across the current model landscape. The optimal default configuration for routine help desk work is Claude Sonnet 4.6, specifically set to low-effort mode. Production teams manage scale by implementing a tiered routing strategy. The flow works like this. Claude Haiku acts as a triage classifier to assign difficulty. Sonnet handles 90% of the ticket volume. The heavy model, Opus, is reserved strictly for tickets flagged as complex. Help desk user experience is gated by latency. A customer waiting 30 seconds for a basic fix will close the chat window, completely invalidating the benefit of profound reasoning. Production systems like Intercom's Fin handle billions of conversations using a single sophisticated agent. While multi-agent swarms are a popular research trend, the largest scale deployments often rely on a single-node architecture. Single-agent setups natively win on latency because there are zero inter-agent handoffs. They win on observability by generating a single clean trace per conversation, and they win on iteration speed because you only have one prompt to update. You should treat subagents as specialized extension points. Reserve them for moments where domains are strictly separable by policy, like isolating sensitive billing data from general technical support workflows. In those cases, the SDK subagent primitive spins up isolated context windows. The billing specialist subagent operates securely, prevents its data from contaminating a separate security workflow, and passes only the relevant answer back to the main agent. Architectural choices must be dictated by hard operational constraints and workload realities, not theoretical aesthetic preferences. A production help desk agent relies on three mandatory imperatives: 5-part prompt modularity, a 3-tier memory separation, and low-effort tiered model routing. When an agent generates a poor response, the surface text is rarely where the systemic bug actually lives. You have to find the upstream layer that failed. A truly intelligent agent is merely the reflection of an airtight, deeply optimized upstream architecture. If this breakdown was useful, subscribe. Then drop a comment identifying the layer in your own agent stack you suspect is making the others look bad. Tomorrow, in Day 5, we move beyond prompt instructions. We will enforce accuracy through citation mechanisms, output validation, and dedicated anti-goal classifiers. Because right now you have an agent you can demo. Tomorrow, we build the guardrails required to actually ship it.